Okay, so right now I'm going to go over some problems concerning acceleration and displacement. Okay. First, just so this isn't completely unknown to you, I'm going to go over some vocab that's going to come up in the later problems. So everything we're doing here concerns two mathematical quantities, scalar and vector. Okay, scalar is basically defined as having magnitude. In essence, that's just having size, in other words. So you could think of scalars as like temperature or mass or time. Vectors are defined as having magnitude and direction. Okay, a good example is any type of force. You think of weight as a force because it has both size and you know it's happening. You know what the direction is. Okay, so any kind of force, you know exactly what's going on with it. Okay. What we're doing today has a lot to do with displacement as well. Displacement, position, speed, and velocity. Displacement is basically what you're saying, it's a vector and it's how far and in what direction. So if you're moving a distance, you're moving how far and in what direction. Basically you got displacement. Position is relatively similar, but position is defined in terms of an origin. So if you have an origin, which is your point O, your final position, your position is defined in terms of that origin. Okay? Now speed refers to position in terms of the rate of change in position. So there's always an origin, so you're always going to have an initial position and a final position. And your rate of change between those is going to be your speed. Velocity refers to both speed, refers to all three of those quantities in terms of your change in position. Here, let me write that on the board so you can see it. Velocity is your change in position per unit time over your displacement. Your displacement is already a change, also per unit time. Okay? So those four quantities are what we're doing. Alright. So when you think of any sort of displacement problem, you're thinking of something moving how far and in what direction. So we're going to say for this, there's an airplane. And it's moving 200 meters per second. So we're going to say this airplane travels for 1 hour. So in 1 hour, 3,600 seconds, 3,600 times 200. So you're essentially going, if you do the math, 720 kilometers total. Correct? You just multiply your 1 hour, convert that to seconds, 3,600 seconds, times 200 to get your meters, seconds, cancel, get 700,000 or so meters, convert that to kilometers, and you get your 720 kilometers. Okay? Now, let's change this It's the basic information now. Let's say that you had a tailwind of 40 meters per second on the way there. So let's say the airplane is going from your origin, just call that point A, and it moves to its final position, point B, 720 kilometers away. Okay, and on the way there, it's got a 40 meter per second tailwind. Okay, if you're trying to now, the problem is you're trying to calculate how far out and back. Okay, so out there, you add these two quantities. That's your speed, 240 meters per second. All you need to go is 720 kilometers. That's your distance. So basically, let's convert that to meters by multiplying by 1,000. 720,000 meters. You're going 240 meters per second. Okay? That's going to take, let's write that where you can see it. That is going to take 3,000 seconds. Convert that to minutes, it's equal to 50 minutes. That's your way out there. On the way back, you assume the same tailwind, so you're going to go 40 meters per second with less speed. It's now a headwind as you're going into it. So your new speed is 160 meters per second. Same distance, 720,000 meters. Your rate is 160 meters per second. Okay? Alright, we're going to try and squeeze this in here. That is effectively 4,500 seconds equals, let's see, math here, 75 minutes. If you're clear where you're going right here, you just have to add these two quantities, get 2 hours and 5 minutes. Out and back with a tailwind on the out part of 40 meters per second, headwind on the way back. So, out and back originally cost about 2 hours. Now it's 2 hours and 5 minutes, assuming these quantities. Alright, now we're going to change the problem just a little bit. Okay. The airplane takes off in the same space, and it's still moving 200 meters per second. That's its initial speed. Alright, now we're going to calculate. Oh, I'm sorry. Now you still got the same distance of 720,000 meters, getting to point B. Say this is the expected point, okay? So, now we're going to assume a side wind on the plane of, let's see, side wind of 60 meters per second, okay? And it's moving this direction. We're supposed to calculate the displacement. So let's call a point X the area where the plane would end up if it did not account for this side wind. So, excuse me, your displacement is going to be this quantity here, okay? So, for every meter it moves in this direction, it's going to move a little bit in this direction as well, because there's a side wind, okay? So right now we know it takes 3,600 seconds to go this distance. It takes 1 hour to go 720 kilometers. We know that already. Okay, for every meter, for every second, it moves up. It moves 60 meters. So basically, what you've got here is just your 60 calculated into this. So, multiplied by 10, basically. Well, that's wrong. You have 36,000 meters unaccounted for in your side wind. That's your displacement right there. This displacement, which is 36 kilometers. Okay, and that's how much you would move in this direction towards your variable x if you did not account for the displacement of the side wind when you took off at A. Okay. We're going to do one more problem. It's a little more complicated. Okay. Do this with an airplane again, because it's easier. So you got an airplane, and it's moving at half the speed of the last one at 100 meters per second. Alright, this airplane is deploying parachutes within this zone, A and B. This is 3,600 meters, let's say. It's an easy enough quantity to work with. So, let's also say the plane is 100 meters above the ground. So you can already tell that this is only to do with the parachuters and how evenly you have to displace them. Okay? So, you have to deploy 20 parachutes in this time. 3,600. Okay? So you got 3,600 meters moving at 100 meters per second. Let's just calculate the speed of how fast you're going to be going. Okay, so you got 36 seconds to deploy 20 parachutes. You're going to be deploying them every 1.8 seconds throughout this zone here. So the first part of your problem is to determine how evenly you have to drop each parachute. Okay? Alright, now we're going to make this a little more complicated. We're going to add a tailwind, okay? So, same distance, 3,600 meters, but there's a tailwind. Let's call the tailwind, just easily enough, 25 meters per second. So we're going to assume now your plane is going 125 meters per second. Okay? So, that's going to equal 28.8 or so. You can see that our last one was 30 here. Because we're going a little bit faster, you're going to have a little bit less time. Still has to deploy 20. And that's your answer. You get 28.8 divided by 20. That's how evenly you will have to deploy each parachute. Okay. Okay. Now because of this tailwind, you're also going to have to drop the parachuters earlier because they're going to be carried a little bit. You can see that if a parachute drops here, and it's going to be carried by a tailwind, it's going to be dropped more evenly. So if you dropped the last one here, it would be outside the drop zone, which is why you have to account for dropping them earlier at about here so that they land within the drop zone due to the tailwind. Okay? So, let's assume parachuter's average speed is 10 meters per second, okay? Per 100 meters, that's a 10-second parachute ride, okay? 100 meters divided by 10 meters per second, 10 seconds. Okay? 10-second parachute ride. But there is a 25 meter per second. Let me write that where you can see it. You can already see it here. 25 meter per second tailwind on each of them. They're traveling for 10 seconds. For every second, they're moving 25 meters in the opposite direction. Can multiply for 10 meters times 10 seconds, 10-second parachute ride times 25 meters per second. So they're going to be moving 250 meters towards their drop zone. So you're going to have to start dropping them 250 meters in advance of point A so that they all can make the drop zone. So 250 meters, calculate that. 250 meters in advance of the drop zone. Your plane is moving at 125 meters per second. It's moving 2 seconds ahead of time, so begin dropping them 2 seconds in advance. Because of this, your drop zone to drop them all as evenly as possible is going to be 1.44 seconds. You can look back at this equation and add 2 seconds to it. Divide by 20, and here's how evenly you're going to have to drop them. So, what we originally got was every 1.8 seconds without the tailwind. But because you're moving faster now, and the parachutes are going to be gliding, this quantity is going to be less, so that you can account for that 25 meters per second tailwind. Okay, thank you.